Bonjour YouTube, je m'appelle Joseph Fourier et je viens d'inventer une transformation magique. Now I'm slightly allergic to Microsoft Excel and I'm not a mathematician, but you can find out a hell of a lot on YouTube, and I've been researching spectral analysis of sound and Fourier transformations. There's this great website where you can upload your own sound samples and then have them go through their spectrum analyzer. So this is the A, 2 octaves above middle C. I made a spreadsheet which essentially represents a sinusoidal curve in a series of steps, and then added second, third, fourth, fifth, sixth harmonics to that and gave them individual amplitude values which we can play about with, and this instantaneously recalculates the amplitude for that harmonic. The fun part of this is that having calculated all the values, we can visualize them in the form of a multi-line chart. So as I change the numbers on on the amplitude, we get different, let's make that a bit smaller, we get different calculations of what the total, the white line represents the total of all of the 6 different bits of harmonic added together. Let's just change the horizontal scale so we can sort of imagine this being a guitar string vibrating. So now we've got the whole thing just represented as if it were a vibrating string. The red line represents the fundamental, the sort of root of the harmonic. The orange is the second harmonic, and so on. So what we've done here is taken a table of amplitude and frequency data and converted it into a visual representation of amplitude versus time, which is the exact opposite of what Monsieur Joseph Fourier did. I chose to break up the sine wave into 130 steps because that is what seemed to produce a relatively smooth curve when represented on a chart. Now, if that one cycle of the fundamental was a note at, say, 329 Hertz, that's an E, then this graph would represent that E note sampled at a rate of 44.1 kilohertz. Now at this point you could be forgiven for asking, Andy, why are you even bothering with this? Primarily it's academic curiosity. I just want to understand how it is that these pickups sound so different, and quite possibly reverse engineer it in the sense of trying to create a visual representation of what kind of frequencies these pickups would be expected to be picking up based on where they are. On this chart, the neck pickup is around about here, which means that it will be completely insensitive to the fourth harmonic. We've seen this before. Fourth harmonic on an open string is just not picked up at all by the neck pickup. The bridge pickup is around about here. Now I changed the dark blue line to be the 16th harmonic, and we would expect the neck pickup to be completely insensitive to the 16th harmonic of an open string. Well, having successfully proved absolutely nothing at all and upset Mr. Fourier, all I've got to do now is to say thank you very much for watching. Maybe next time I'll find a way of turning those sine waves into actual sound. That'll be an interesting challenge. Thanks, bye!